This is an example of a flash distillation column or a flash drum. This is taken from example 21.1 from the Turton et al. Chemical process design textbook. So what we have here is a mixture of propane, benzene, and cumene is being flash separated. We're told that the feed is 200 kilomoles per hour and the composition is 5 mole percent propane, 51 mole percent benzene, and 44 mole percent cumene. We're told that we can assume that Raoult's law is valid, and we're told that the flash conditions, and so these are the conditions in the flash drum, are 90 degrees C and a pressure of 1.7 bar. And we are asked to find the vapor and liquid flow rates and the compositions of the vapor and liquid flow streams. And so one of the most important things to consider in this problem is what kind of vapor-liquid equilibrium we can work with. And we were told that we can assume that Raoult's law is valid. And so what that means is that we have ideal gases and ideal liquids. And so this means that there are relatively few intermolecular interactions that we need to worry about with the species, that these are well-behaved chemical species and act essentially as if they do not interact with the other chemical species. And so what that means is that the partial pressure of each species is equal to the mole fraction in the vapor phase times the total pressure, and that in the liquid phase there are essentially no significant interactions, and so the activity coefficient of each component is equal to 1. And so Raoult's law can be written as Y sub I times P. The total pressure is equal to Xi, which is the mole fraction in the liquid phase, times the saturation pressure of that component. Another equation that we can use from that is the K value. And since Raoult's law is valid, the K value is, well, I should say the K value is defined as Yi over Xi, the relative volatility of each component. And if Raoult's law is valid, that simplifies to simply P sat of that component divided by the total pressure. So this is a flash drum. We need to calculate the vapor liquid flow rates coming out and the mole fractions of each component in the liquid and vapor phase. So I'm not going to go through the derivation of all the equations that are used to analyze these flash drums. I'm simply going to work through the problem as you would need to do so. So one of the first things that you should do is assemble your properties that are needed. We are given the mole fractions, and note that I am using 0, 1, and 2 as my indices for my components instead of 1, 2, 3. This is simply because MathCAD, like other programming languages, starts their indexing at 0 instead of 1. So anyway, the first thing to do is to get the Antoine equation constants, and those were given to you in the textbook, and so I'm just going to drag them over here. So make sure you get the units right, and pay attention to the units that are used in the Antoine equation. In this case, it was degrees Celsius, and the pressure unit was torr, or millimeters of mercury. Also be careful about the logarithm base. Some Antoine equations will use natural log, but this one uses a logarithm of base 10. And so once we get that information entered, I usually calculate the saturation pressures for each of the components. And so here I have the Antoine equation, and remember we have to have things dimensionless and add the dimensions afterwards. So I'm using a Kelvin in my calculations. So I had to convert to Celsius and divide by Kelvin to make everything dimensionless and work out with the math. And so I usually check these calculations and just make sure everything is done correctly. I need to move this down a little bit. we can, if I can, there we go. We can look at the calculations and make sure things make sense and we haven't made any silly mistakes. And so remember, component 0, first component in this list is propane. It has a very high saturation pressure, which is what we would expect. And the other components, the benzene, the cumene, have a much lower saturation pressure at this temperature, which again is what we expect. So we should be good there. Now, when you're doing flash calculations, in this problem, the temperature and pressure were given to you. And that is fine. We were told that under these conditions, we will definitely have both a liquid phase and a vapor phase being produced at the flash drum conditions. But one of the things that you can also do in case you do not know what the pressure and temperature are, maybe you need to do some exploration, is you need to make sure that yes, indeed, two phases will result under these conditions. And so what you can do then is a lot of times that the temperature is known, and so we'll assume that the temperature is known, and then we can calculate both the bubble point and the dew point pressures at this temperature to make sure that our pressure that our flash drum is operating at is in between those bubble point and dew point pressures. We could also do the other calculation where we fix the pressure and then we see if the flash drum temperature is between the dew point temperature and the bubble point temperature. I'm going to do the bubble point calculation and dew point calculation, since those are a little easier to implement here and faster, and this is really supplementary material. And so what we do is we set our liquid phase concentration equal to whatever is coming in. And again, I just have a couple little checks here to make sure that there's no silly mistakes being done in assignment of the variables. Our bubble point pressure calculation, if you look in your thermodynamics textbooks, when we are dealing with Raoult's law, we don't have to worry about any activity coefficients, and so it's just the sum of the mole fraction times the saturation pressure of each component. And so we get 2.5 bar. And remember, our flash drum is operating at 1.75 bar. And so that is lower than our bubble point pressure, and that is good. And so we can also calculate the compositions. Again, this is not necessary, but sometimes I like to do these things just to make sure everything is going okay. And we can see that that first bubble of vapor that is going to form, it should be enriched for the most volatile component. And indeed it is. Propane in this system is going to be the most volatile component. And you can see that that first bubble of vapor is significantly enriched for the propane. Next, we can do the dew point calculation. So the dew point calculation is a little bit more involved, and as far as the math that goes. So we set our initial our vapor compositions to the inlet conditions for the flash drum. We then need to do a guess for the dew point pressure and the liquid phase compositions. And so a good guess for the dew point pressure is just a weighted average of the mole fraction times the saturation pressure. And so we get a, let me put this in bar, we get a value of about 2.5 bar, which is similar to what we see up there. And then we do an initial guess of the compositions of that first little droplet of liquid that is going to form. So those are our initial guesses, and then I'm going to use a solve block, not an iterative method. I'm going to use a solve block in MathCAD to actually calculate the dew point pressure and the compositions. And so we've got four unknowns. We've got the dew point pressure, and then we've got the mole fractions in the liquid phase, x 1, 2, or 3, or I should say 0, 1, and 2 to be consistent with my notation. So we have four unknowns. That means we need four equations. And so our four equations come from the number 1, the equilibrium overall pressure. The dew point pressure is 1 over the sum of the vapor phase mole fraction divided by the saturation temperature. Again, you can look in your thermodynamics textbook to get these equations. And then we have an equilibrium relationship for the liquid phase mole fractions. I could have written this also for x sub 2, but I used the fact that the sum of the mole fractions have to equal to 1 as my fourth equation. So then I used the command in MathCAD to find the values of my liquid mole fractions and my dew point pressure, and I get a dew point pressure of 0.29 bar. You can see that of course is lower as expected, and that our flash pressure in the drum is 1.7 bar, definitely in between the dew point and bubble point pressure. So that was extra. That was not needed for this particular problem, but there may be cases where you have to do that check for your flash drum calculations to make sure that it's something that you've got something you're starting with that is going to work. So now we can actually start with a flash calculation. And so the first thing I'm going to do is define the relative volatility in terms of the saturation pressures. Bring over this just to make sure that we know what we're dealing with. The next thing that I'm going to do, and again, I'm not going to go through the Rachford-Rice and all of the other equation derivations, but I just want to make sure we understand what our unknowns are. So we're given the feed and the inlet composition, we're given the temperature and pressure, and so you can go through the Gibbs phase rule and you can see that once the pressure and temperature are defined, there are 0 degrees of freedom. So our system is defined. We can actually get a solution for this. As far as the number of unknowns, we've got the vapor flow rate, we've got the liquid flow rate, we've got the X liquid phase mole fractions and the Y vapor phase mole fractions. There's 3 of those mole fractions in each of the streams, and so we have a total of 8 unknowns. So that means we're going to need to come up with 8 independent equations to solve this system. There's multiple ways you can do this solution. I'm going to take advantage of the solve blocks in MathCAD, so we don't need to do an iterative calculation like one would implement in a more conventional programming language. And so what that requires is that we make initial guesses for all of these 8 unknowns. And so I entered a guess of 50 kilomoles per hour for the vapor phase flow rate, and then of course the liquid phase flow rate will be 200 minus that, so I didn't write that down, but that's 150 kilomoles per hour for L. And then I gave some guesses for the liquid phase mole fractions and the vapor phase mole fractions. And if you're using the Rachford-Rice approach, that equation is relatively I should say stable, and you don't have to worry about coming super close in your initial guesses to your final solution. You'll get a good convergence. There's some other methods you can use to solve this problem that are a little more sensitive, and you have to be a little more careful about how you guess. But it's good to enter something that's reasonable. You can see even here I should fix this. This should be 0.6 because I want everything. Oops, 0. This is not showing up. 5.5, so that everything adds up to 1. That will be ideal. Although you'll still get the right answer, it turns out, even if you do not have your mole fractions summing up to 1. So I've got 8 unknowns. I have to come up with 8 equations, and so I'm going to bring everything over in block. I have my given statement in MathCAD. This is MathCAD, so-called programming language, and I've got my 8 equations here. The first equation here is the Rachford-Rice equation, and so this is derived in most equilibrium stage op textbooks and thermodynamics textbooks. This is basically a material balance for or I should say a material / equilibrium balance for each component. I have my overall material balance, which is just that the total flow rate in is equal to the flow rates out. And then I have my individual equilibrium relationships, along with the fact that the mole fractions have to sum up to 1. And so I have 1, 2, and then 1, 2, 3, 1, 2, 3. I have 8 equations for my 8 unknowns. And so then I can use the MathCAD command, which is the find command, to find the values of L, V, X, and Y to solve this problem. And once I do that, I get my answers. And so the liquid, remember, coming in was 200 kilomoles per hour. About 192 kilomoles per hour is going to leave as liquid, and about 8 kilomoles per hour is going to leave as vapor. So about 4% of my feed is going to exit in the vapor stream. And we can look at the mole fractions of each. Remember that propane, benzene, and cumene, and we would expect that since propane is much more volatile than the other components, that it should be at a low mole fraction in the liquid phase. Hopefully we are operating our flash drum at such a temperature and pressure, and indeed it is at a low mole fraction. And then for the vapor, we would expect that it would be enriched for the most volatile component, and indeed it is enriched for the most volatile component. Notice, however, that this is not necessarily a nice clean separation. You can see there is a lot of benzene and a little bit of cumene that is coming along in this. If benzene were a valuable component, maybe you would want to adjust the conditions to get rid of or have more of that benzene go into liquid phase. Or if a single stage flash drum is not adequate to do this separation, you want a much cleaner, finer separation, maybe you should go to a distillation column. But this illustrates the flash calculation when you can use Raoult's law.